Good morning, dear students. Yes, yesterday we finished our discussion with the introduction of first equation of motion, and I told you this is actually the definition of acceleration from which we uh, make this equation by rearranging the terms. If I rearrange the term, this becomes v is equal to u plus at. This equation is known as the first equation of motion, in which v is always the final velocity, u is always the initial velocity, a is always the constant acceleration given or to be found, and t is the time for which the object has moved. Let's say an object is initially at rest. It starts moving and it accelerates for a certain time, let's say 5 seconds or 10 seconds. So for whatever time it accelerates, we multiply these two and calculate the final velocity it has acquired. The same equation can be used for all those situations where an object is falling freely or is thrown upward, because the acceleration then becomes the acceleration due to gravity. Acceleration due to gravity. So while this equation is used in situations when the object is moving on the road, this equation is used when the object is falling freely or is thrown upward. So for vehicles, for trains, for planes moving with a constant acceleration, on the road or in any situation, we use this equation, because the acceleration is not the acceleration due to gravity, because the object is not falling freely. So for any other type of motion in which the object is having some constant acceleration different from 9.81, we use this form of equation, but this readily takes this form 9.81 if the object is known to be falling freely or is thrown upwards. The difference is, if I throw upward, this positive sign becomes negative. So we apply this equation on a few situations to make clear how we make use of it. A point that is that should be remembered is, this initial velocity is always 0 when object is dropped from a certain height. 0 for objects dropped from a certain height. Like if I leave this object, this marker, from this height, the initial velocity will be taken 0. But the same object, if it is thrown upward, this is not 0, because no object is expected to move upward with 0 initial velocity. So initial velocity in the case of an object thrown upward is taken that velocity with which it leaves your hand. So if you throw an object upwards, or you fire a bullet in the upward direction, you throw an arrow upward, the initial velocity is that velocity with which that object leaves that point from where it is thrown. If it's a stone you are throwing upwards, the initial velocity is the velocity with which the object leaves your hand. And therefore, if it is non-zero because you are throwing it upward, the final velocity at the maximum height can be taken 0. These are basic ideas, and I hope you are familiar with these things. I repeat again, this equation contains an acceleration which should always be constant, otherwise this equation cannot be applied. and initial velocity and final velocities, they may be known, and they ask you to calculate the time for which the object has moved. Let's say the object is already in motion. It is moving with 2 meters per second, and with constant acceleration of 10 meters per second square, it acquires a certain speed, which is also known. You have to calculate the time in which that change has taken place. So that could also be done easily. I will come back to this equation again when we have a few questions to solve, but let's move on to the next equation, what it looks like and how it can be derived. Second equation of motion. Second equation of motion can be derived from two equations. Equation number one, which is this, using V is equal to U plus AT, and an equation which is known as a supplementary equation, which is displacement is equal to U plus V over 2, which is the average of the two, multiplied by the time for which the object has moved. If there is some variation of velocity, initially you have a different velocity, then it becomes V. We take the average of the two and multiply it by the time, the total time in which the object has moved. This product gives us the displacement that the object has covered. Sometimes they use the term distance, and sometimes you use the term displacement. It is same because in all these situations, the object should be moving along a straight line. The object should be moving along straight line when you apply this equation. The object should be moving along straight line when it is falling freely, when it is thrown upward. This equation is applicable for straight line motion, because when the object rotates or move in a circle, we have different set of equations. So all these equations have to be applied for straight line motion. This is equation number one, and this is a supplementary equation. If I use this V in this equation, use this value here in place of V, so S is equal to U plus AT. U plus AT. I have replaced this V by this U plus AT divided by 2 into T. When I simplify this all, it becomes 2U plus AT, and if I multiply this T by these two terms, this becomes 2UT plus AT square over 2. And when I separate these two terms, it becomes UT plus half AT square, because when I divide this term by 2, this cancels, and when I divide this term by 2, it becomes 1 over 2 AT square. S is equal to UT plus half AT square is the second equation of motion. Second equation of motion shows how far the object has gone. This is displacement. Displacement. If it was moving with certain initial velocity, and we know the time for which the object has moved, and this is the constant acceleration like always, and this is again the same value of time for which the object has moved. This second equation of motion is clearly applicable in all those situations in which we know the initial state of motion of the object, we know the constant acceleration for which the object has moved, we know the time for which the object has moved, and we can calculate the displacement. And if we know the displacement, we know the initial state of motion, and acceleration is known, we can calculate the time. Usually this equation is very helpful in calculating the time for those situations in which the object is initially at rest, and we know the acceleration for which it has moved and the displacement or the distance it has covered along the straight line. That means it is very useful for those situations in which the object is dropped from a certain height where initial velocity is taken 0. So this term disappears. So s, which is the height in that case through which the object has fallen, this a becomes the acceleration due to gravity, 9.81, and we can easily calculate the time it has taken to fall through a known distance. So if the only quantity that we know is the height through which the object is falling, we can easily calculate the time it has taken, because we know the initial velocity. Even if it is not stated in the question, they simply say it is dropped. So when the object is dropped from a certain height, the initial velocity is 0. And they are not going to tell you what acceleration it will go through, because if the object is falling freely, if the air resistance can be ignored, the acceleration is the acceleration due to gravity, which is 9.81. So they will ask us to calculate the time it has taken to fall through that distance. So initial velocity is 0, understood, and a is 9.81 equal to gravity, the acceleration due to gravity. So t can be calculated for all those situations. This is particularly useful in this situation. Now the third equation of motion. Third equation of motion can also be derived from the same two equations. Again, v is equal to u plus a t, and s is equal to u plus v over 2 into t. This time, instead of eliminating v from this equation, we eliminate t, and we go back to this equation and we rearrange, and when I rearrange this same equation, I get t is equal to v minus u over a. So this is, I have basically rearranged this equation. I have taken this u to this side, so v minus u, and then divided v minus u by this a. So t remains and becomes the subject of this equation. You replace this t here. So it becomes u plus v over 2, and this becomes v minus u over a. These two things, u plus v or v plus u and v minus u, they are actually an identity, a well-known identity in maths. This is 2a because these two multiply. This is v plus u multiplied by v minus u. This is actually square of difference of two squares, v square minus u squares, a well-known identity in algebra, divided by 2a, and this is s. So when I bring this 2a to this side, the equation becomes 2as is equal to v square minus u square. So this is the third equation of motion, which is sometimes written in this form, v square is equal to u square plus 2as. But this is mostly used in this form because this is more convenient. 2as is equal to v square minus u square. Again, you can see there is no t in this equation. So in those situations where time is not known, but we know the acceleration, we know the displacement the object has gone through, and we know initial velocity, and we have to find the final velocity. This is convenient. So in all those situations in which the object is starting from rest, let's say, and we know how far it has gone, what is the acceleration with which it has been moving, and we can easily calculate the final velocity. So acceleration multiplied by the displacement through which the object has gone into 2 under root, that gives the final velocity if we know the object is initially at rest. So this goes, there is no u square, v is simply 2as under root. So again, when the object is falling freely, because there are so many questions in which the object is thrown upward or it falls freely, so these equations will be particularly useful in all those situations. So these are the 3 equations of motion which have a variety of uses, and we will apply them to various questions. I will share with you many questions, the worksheets in which these questions, these equations will be applied. You can practice so many questions, particularly from the multiple choice questions, because there is a variety of equations you can find. But let's discuss them for a few simple situations. An object is at rest. Let's say it's a car. A car starting from rest acquires a speed of 25 meters per second in 10 seconds. Calculate its acceleration. Calculate its acceleration. The best way to approach the problems in which we have to find the acceleration or the final velocity or initial velocity or displacement, the best way to approach is to see what is given and what is to be found. We make a list of these things, and by making the list of those quantities, we can identify the equation that we can apply. For example, starting from rest readily gives us the idea of what u should be. U, the initial velocity, it should be 0. It acquires a speed of 25 meters per second. That means this is something final, and there is no other speed after it mentioned in the question. So this should be the final speed it has acquired. And obviously time is also mentioned, so t is equal to 10 seconds. What is to be found is acceleration. Now if you look closely at all these quantities, they all fit very well into this equation. V is equal to u plus at. So that means this is 25, this is 0, this is to be found, and time is 10 seconds. And when you rearrange all this, A is equal to 2.5 meter per second square. So this is the acceleration with which the object has moved. Now, if they ask us to calculate the displacement, how far the object has gone. So if this is part one, in the next part of the same questions, they might ask you to calculate its displacement. Now, there are two equations other than first equation of motion in which displacement is mentioned. In second equation of motion, S is equal to ut plus half at square. This could be used, and this will be easy, particularly if initial velocity is 0. So this term disappears and we are left with a simpler form of this equation, which is this. So remember, in all those situations in which initial velocity is 0, finding displacement with the help of second equation is particularly useful and convenient. So S will be equal to 1 over 2 into 2.5. We have just calculated the acceleration, multiplied by the time for which the object has been moving, and that is 10 seconds. So 10 squared mean 100. So if this is 1.25, if I cancel this 1.25 multiplied by 100, this gives me 125 meters. That means the object which has moved initially from rest and has acquired a speed of 25 meters per second in 10 seconds, it has covered a distance of 125 meters moving along a straight line. The same calculation can be done with the third equation as well. And just to show that it can be found from third equation, 2as is equal to v square minus u square. This will be 0 because the object is initially at rest. That means v square, the final velocity that it acquired was 25. 25 squared is 625. This is 2 and acceleration is 2.5, and this is S. This is 5 times S is equal to 625. So again, S is equal to 125 clearly. So same answer as expected from second equation and from third equation as well. Here we made use of the time for which the object has moved and the acceleration, whereas in this equation, no need for time. We just have to mention the final velocity that it acquired and the acceleration with which it kept moving throughout the constant acceleration. So both equations should lead to the same answer. So this is just a simple example of the equations of motion. Remember, equations of motion are applicable in all those situations in which the objects are moving along a straight line and they are moving at a constant acceleration. So in all those situations in which the object are falling freely, they are thrown upward, they are also fulfilling that condition. So equations can be applied to objects falling freely or thrown upward. This is it for today. We'll share a few questions with you, inshallah, in the next week. Thank you for today.